A star has already died. Its fires went out long ago. It cannot burn, it cannot fuse, and it should sit in the dark forever as nothing more than a cooling ember, roughly the size of Earth. And yet, tonight, we are going to watch this dead star explode. Not from the inside, the way you might expect. Not from some slow build-up deep at its core. Instead, the explosion begins on its surface, in a thin, stolen skin of helium, and then something almost impossible happens. That first outer blast turns inward, races through the star, squeezes its buried heart with the force of a hammer, and forces the corpse to detonate a second time from within. The dead ignite themselves. By the end, you will understand exactly how. Before we go any further, if you enjoy these deep dives into the strangest corners of the universe, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Imagine a star. Not one of the giants that spans 1,000 times the width of our own sun, but something modest, something ordinary. A star roughly the size of the one you see rising in the morning sky, the one that lights your day. This star, if you could go back and watch it during the calm middle stretch of its life, would have looked almost boring. It sat in its own patch of the galaxy for something on the order of 10 billion years, doing nothing but slowly fusing hydrogen into helium in its deep core, converting a tiny fraction of its own mass into pure energy every second, and radiating that energy outward as light and heat. The pressure this fusion produced was what kept the star from falling in on itself. Gravity constantly tries to crush the star inward, and the only thing that stops the collapse is the outward push of heat and radiation from the nuclear reactions inside. As long as those reactions run, the star endures, but no fuel lasts forever. Eventually the hydrogen at the star's core is used up. When that happens, the story does not end, but it does change dramatically. Fusion moves outward into shells around the depleted core, and the star begins to change shape. It swells, it reddens, it becomes a red giant, a bloated version of itself, hundreds of times larger than it was in its youth. If our own sun were to do this today, its outer layers would engulf Mercury, then Venus, then quite possibly the Earth as well. Inside that red giant, helium briefly fuses into carbon and oxygen, but helium burns fast, and when it runs out, a star of modest mass cannot compress its core hard enough to fuse those heavier elements. Those next steps require more massive stars. Our modest star cannot reach them. At that point, the star gives up. Its outer layers, no longer supported from below, drift away into space. They form a soft, glowing shell that we call a planetary nebula, though the name is a historical accident and has nothing to do with planets. And in the center of that fading shell, exposed and cooling, sits the object we're here to talk about tonight. The naked core of the dead star, the white dwarf. Now, you have to understand something very carefully about what a white dwarf actually is, because your instinct is going to be wrong about it. Your instinct is going to tell you it is still a star, just a smaller one. It is not. Or at least, not in the way you were picturing. A white dwarf is what is left after all the nuclear fusion has stopped, permanently. There is no burning going on inside it, and there is no ongoing chain reaction. There is no source of new energy anywhere in the entire object. It is not powered by anything. It is simply sitting there, holding its ancient heat, radiating that heat into space, slowly cooling over a timescale so long that no white dwarf in the universe has yet had time to fully fade into a cold, dark object. The universe itself is not old enough for that. Every white dwarf that has ever formed is still radiating today. Dimmer than it once was, but still detectable in principle. And this object, this dead core, is stunningly dense. A typical carbon-oxygen white dwarf holds a substantial fraction of the sun's mass, often around half or 2/3 of a solar mass, and it packs that entire mass into a sphere about the size of the Earth. Think about that for a moment. All the mass of the sun, which is more than 300,000 times the mass of the Earth, squeezed down into a volume no bigger than the planet you are standing on right now. A single teaspoon of white dwarf material scooped from its interior would weigh several tons on Earth's surface. If you could somehow set it down on your kitchen counter, it would punch through the counter, through the floor beneath, and continue falling toward the ground with a weight so extreme it would deform anything it landed on. This is what death does to a star. It condenses it into an object where the ordinary rules of matter no longer entirely apply. And that is really the point. Because normally, when you compress ordinary matter that hard, it heats up. That is how gas pressure works in the world you are used to. Squeeze a gas and it warms. Warm a gas and it pushes back. This is why the atmosphere behaves the way it does, why hot air rises, why a bicycle pump gets warm as you compress the air inside it. Regular matter is regulated by a simple, comforting rule. Pressure and temperature are tied together. If one goes up, the other tends to follow, and the two of them together keep the material stable and predictable. But inside a white dwarf, this normal relationship breaks. The matter there is no longer normal. It has been squeezed so hard by the crushing weight of a whole star that a completely different kind of physics takes over. And to understand the double-detonation supernova we're exploring tonight, you have to understand this weirdness, because it is the entire reason the story can end the way it does. The entire mechanism hinges on this one strange property of degenerate matter. Let me explain it as clearly as I can. Inside an ordinary atom, most of the space is empty. There is a tiny nucleus at the center, and around it, at a huge distance in atomic terms, a cloud of electrons. Between the electrons and the nucleus, there is nothing but vacuum. If you scaled a single atom up to the size of a football stadium, the nucleus at the center would be about the size of a small marble on the 50-yard line, and the electrons would be moving in an enormous cloud filling the entire stadium. That is how empty ordinary matter really is. Under normal conditions, if you push atoms closer together, their electron clouds start to overlap, and the atoms resist. This is why solid objects feel solid. It is not that the atoms are actually touching. They almost never touch. What you feel when you push against a table is the electric repulsion between the electron clouds in your hand and the electron clouds in the wood. That resistance is what makes matter behave the way we expect. But if you push hard enough, if you press matter with the crushing weight of a whole sun, you can start to overcome even that repulsion. You can push atoms so close together that their electron clouds are no longer separate. The electrons stop belonging to individual atoms and start acting like a single shared sea, flowing freely through the material. The nuclei, stripped of their neat little orbital shells, sit crammed together in a lattice, packed almost as tightly as they can be packed. This is what the interior of a white dwarf looks like at the subatomic level. It is not a plasma the way the inside of the sun is a plasma. It is something much stranger. It is called degenerate matter. And in degenerate matter, a completely different force takes over as the source of resistance. It is not thermal pressure, not the ordinary pushback of hot gas. It is a quantum mechanical effect that comes out of a rule in physics called the Pauli exclusion principle. In plain language, the rule says that no two electrons can occupy the exact same state at the exact same time. They can be close together, but they cannot be identical. They must each have their own slot, their own little corner of possibility space. Now, when you crush electrons together as tightly as they are inside a white dwarf, you fill up all the low energy slots first, then the next lowest slots, then the next, and so on. Every electron has to sit in a slot no other electron is using. And to fit them all in, the electrons at the top of the stack end up moving extremely fast, not because they are hot in the usual sense, but simply because there is no lower energy state left for them to occupy. They are packed like people in a crowded elevator, each one shoved into whatever gap remains. And the collective pushback from all those electrons, all of them refusing to share a state, all of them moving at enormous quantum mechanical speeds, is what holds the white dwarf up against its own gravity. This resistance is called electron degeneracy pressure. And here is the crucial thing about it. The thing that matters more than anything else in tonight's story. Electron degeneracy pressure does not care about temperature. Or at least, not in the way ordinary gas pressure cares. Ordinary gas pushes harder when you heat it. That is the rule of everyday matter. Heat causes expansion. Expansion cools things down. It is a natural thermostat, and it is the reason ordinary stars are stable. If the core of a normal star suddenly got a little hotter, it would expand a little, and expansion would cool it back down. That negative feedback loop is what keeps a star from either fizzling out or exploding every time something inside it hiccups. But degeneracy pressure does not obey that thermostat. It depends almost entirely on density, on how tightly the electrons are packed. Temperature, when you heat degenerate matter, has almost no effect on the pressure. You can pour heat into it, and the pressure barely changes. The material does not expand. It does not cool itself off. It just sits there, getting hotter and hotter, while the degeneracy pressure keeps holding it up, regardless of what the temperature is doing. Now, why does this matter? Why is this a horror story instead of just a physics footnote? Because ordinary stars are protected by that thermostat. When something ignites unexpectedly inside a living star, when a fusion reaction begins in a place it should not, the material heats up, expands, cools down, and the ignition is smothered. The star is safe. The runaway is prevented before it can really start. It is like trying to light a fire in a room, where the walls automatically pull back and let the air rush in every time the temperature rises. The fire has no chance to build. But in degenerate matter, if something manages to ignite, if some tiny region of the material begins to fuse, the heat pours in with nothing to absorb or dissipate it. The absent thermostat now becomes the enemy of the star's own survival, and as it gets hotter, the fusion reactions speed up dramatically because nuclear reaction rates are exquisitely sensitive to temperature. A modest jump in temperature can multiply the reaction rate by thousands, and each jump in reaction rate produces more heat, and that heat drives the reactions faster still, and there is no relief, no feedback, no expansion, no cooling. The temperature just keeps climbing, doubling and redoubling, until the reactions are running at speeds that would tear an ordinary star apart in seconds. This is what astronomers mean when they say ignition in degenerate matter goes runaway. It is not a metaphor. It is a real, physical, unavoidable consequence of the difference between degenerate matter and ordinary gas. Ignition inside a white dwarf is not like lighting a candle. It is like throwing a match into a warehouse full of gasoline. Except in the warehouse, you at least get the fire spreading outward through open air. In the white dwarf, there is no open air. There is nowhere for the fire to go. And every kilogram of nuclear fuel around the ignition point wants to burn. And there is nothing physical stopping it from doing so, all at once. That runaway is the beating heart of every thermonuclear supernova. It is why a white dwarf, once ignition begins, cannot simply flare up and settle down again the way an ordinary star can. It has no thermostat. Once the reactions start, they do not stop until either the material is used up or the star tears itself apart from the pressure of its own liberated energy. So the white dwarf is a bomb. That is really the honest way to describe it. A bomb made of degenerate carbon and oxygen, held together by a strange quantum pressure that ignores temperature entirely, waiting for something, anything, to light the fuse. But here is the catch, and it is a crucial one. That fuse cannot light on its own. A white dwarf, left alone in space with no companion, no external source of new material, is one of the most stable objects in the entire universe. It has no fuel that it can access on its own. Its interior is degenerate carbon and oxygen, but the temperature there, though extraordinarily high by everyday standards, is not high enough to force those nuclei to fuse. Carbon fusion requires stunning conditions, temperatures approaching 1 billion degrees, densities beyond anything you can imagine, pressures greater than anything a passive object can generate on its own. A quiet white dwarf, cooling slowly for billions of years, never even comes close to those conditions on its own. It just sits there, slowly cooling, slowly fading, getting a little dimmer every million years, but never on any timescale you can meaningfully speak of, doing anything dramatic. So we have a paradox. We have an object that is essentially a stellar-scale bomb, primed to run away catastrophically if it ever ignites, but that has no way to ignite by itself. It cannot burn its own carbon. It cannot generate the temperature it needs to trigger the chain reaction inside itself. It sits in the dark, cold in comparison to what it once was, holding a treasure of nuclear fuel it will never spend without help. For it to explode, something outside must reach in and light it. And that brings us to the specific weirdness of tonight's story. Because most people, when they hear about a white dwarf blowing itself apart, picture the ignition happening deep inside, near the center. That is the natural intuition. A bomb ignites at its heart, an explosion begins at its middle, the star burns from the inside out. And this picture is not wrong for all thermonuclear supernovae. There are proposed pathways in which the ignition really does begin near the core, after long, slow accretion of material builds up the density in the interior until the carbon there finally lights. But there is another pathway, and it is the one we are here to follow tonight, and it flips that natural picture upside down. In this pathway, the ignition begins not near the middle, but on the outside, not deep in the core, but in a thin layer draped across the surface of the white dwarf like a stolen coat. The first fuse to catch is not carbon inside the star, but helium sitting on top of it, delivered from a companion in a nearby orbit. And when that outer layer ignites, when the helium at the surface begins to burn, it does not simply flare and fade. It sends a shockwave crashing inward through the white dwarf. And that shockwave, if the geometry is right, does something almost unbelievable. It squeezes the core of the star hard enough from the outside in to force the carbon inside to ignite as well. 2 detonations, one right after the other. The first outside on the surface, the second inside in the core. Both of them belonging to a single, unfolding event that plays out in seconds. That is the double detonation supernova. That is the sequence we are here to understand. But before we can get to that, we need to be very precise about one more piece of vocabulary, because it will matter a great deal when we start talking about how the shock waves behave. When astronomers say the word detonation, they do not just mean explosion in a loose, everyday sense. They mean something specific. And they distinguish it from another kind of runaway burning called a deflagration. The difference between these two is subtle at first, but it turns out to be enormous. A deflagration is a burning front that spreads through material by ordinary heat transfer. The flame heats the fuel next to it, that fuel ignites, and the front creeps forward at speeds far below the speed of sound in the material. A candle flame is a deflagration, a brush fire is a deflagration. It is the kind of burning most people are familiar with, and it can be surprisingly fast, but it is always slower than the speed at which pressure information travels through the burning material. That means the material ahead of the flame has time to sense the flame coming. The gas expands, it moves out of the way. And this ability to expand is what gives a deflagration its characteristic tempo. Sometimes fast, sometimes slow, but always in a kind of conversation with the medium it is burning through. A detonation is different. A detonation is a burning front that is locked to a shock wave. The shock leads. The burning follows right behind it, powered by the compression the shock creates. And crucially, the shock moves at supersonic speed, faster than any pressure signal can travel through the material. The fuel ahead of the shock has no warning. It cannot expand. It cannot move out of the way. The shock slams into it, compresses it, heats it, and ignites it, all in a fraction of a second, and the burning that follows releases energy that helps drive the shock forward. It is a self-sustaining supersonic wave of destruction, and it is enormously more violent than a deflagration. In the context of a white dwarf, this distinction is life or death for the star. A deflagration inside a white dwarf might burn part of the star's fuel while leaving the rest intact. Some proposed models involve a deflagration that eventually transitions into a detonation, or a deflagration alone that only partially disrupts the star and leaves a strange half-burned remnant behind. But a full detonation, once it takes hold in degenerate matter, is essentially unstoppable. It sweeps through the fuel almost instantly, releasing energy at a rate the star cannot possibly absorb or contain. And the total energy released can exceed the gravitational energy holding the star together, which is another way of saying the star simply blows itself apart, top to bottom, inside to outside, with nothing left behind but expanding gas. And here is the thing you should hold on to. In tonight's mechanism, in the double detonation scenario, both of the burning events are true detonations. Not deflagrations, not slow burns, supersonic shock-driven runaway thermonuclear waves, one in the helium on the surface, and one in the carbon in the core, and they are linked. The first causes the second. That is what makes this specific pathway so different, and why the outer surface, not the deep interior, is where the story really starts. But we are getting ahead of ourselves, because before any of that can happen, before there is any helium sitting on the surface at all, before there is any detonation of any kind, we have to answer a simple question. Where does the helium come from? A white dwarf, alone in space, cannot produce it. It has no active fusion. It has no way to gather it. The only way that helium can appear draped across its surface, ready to be lit like an outer skin of fuel, is if something else, some nearby object, some living companion, hands it over. And that is where our story is about to turn. Because the double detonation of a white dwarf is never really the story of one dead star acting on its own. It's the story of two stars entangled in a shared orbit, one of them long dead, the other still very much alive and shedding material. It's the story of a slow theft carried out across cosmic time, of matter falling gently onto a corpse, of pressure building up in a thin skin at the surface, and of the moment when the corpse, quietly for millions of years, finally accumulates just enough stolen fuel that the outer layer is ready to ignite. The moment when the dead ember, unable to light itself, finally receives a match from somewhere else. Because remember what a white dwarf actually is. It is a bomb. Not a metaphorical bomb, but a real, physical, nuclear one, held stable only by the strange quantum pressure of its degenerate electrons, waiting, effectively forever, for a trigger, unable to provide that trigger from within. And the source of the trigger, the moment when the long silence finally ends, is what we turn to next. Most stars in the galaxy are not solitary the way our sun is. When you look up at a bright point of light, your instinct is to picture one lonely sphere of fusing gas. But that instinct is misleading. A large fraction of all stellar systems in the galaxy, roughly half or more depending on stellar mass, are actually pairs, triples, or more complex arrangements. 2 or 3 or more stars, bound together by their own mutual gravity, orbiting a common center of mass, dancing around one another for the entire span of their lives. This matters enormously for our story, because a lonely white dwarf, adrift in interstellar space with no neighbor, is safe. It has nothing to steal. Nothing can be handed to it. It will cool and dim for 100 billion years, and never do anything at all. But a white dwarf with a companion, a white dwarf locked in a close orbit with another star, is a very different object. That white dwarf has access to material it cannot produce itself, and depending on what the companion is, depending on how close the orbit is, depending on where the companion is in its own evolution, that stolen material can, over millions of years, become the very trigger the white dwarf has been unable to provide for itself. So, who is the companion? In the specific scenario we are tracing tonight, the companion has to be an object that can deliver helium. That is the raw ingredient the double detonation mechanism needs, a layer of helium sitting on the surface of the white dwarf. Ordinary hydrogen from a normal companion is not quite what this scenario is asking for, at least not directly. What we need is helium, and there are several types of companion that can supply it. The cleanest possibility is another star that has already burned through its own hydrogen, but has not yet died. A star whose outer envelope has been stripped away, exposing a helium-rich interior. Astronomers call these helium stars, and they exist. They are typically hot and blue, smaller than the Sun, with surfaces composed mostly of helium because their hydrogen was either burned in fusion or lost to a previous companion. A helium star in a close orbit with a white dwarf is a very natural donor. It has helium in abundance. It is right next door. And its own strong stellar wind, or the sheer proximity of its outer layers to the white dwarf's gravity, can peel helium off its surface and hand it over. Another possibility, and this is one that has attracted a great deal of attention in the last few decades, is a companion that is itself a white dwarf. A helium white dwarf, to be specific. That is the compact remnant of a star that was too small to ever fuse helium into carbon. Instead of carbon and oxygen inside, it has helium. And when a carbon-oxygen white dwarf and a helium white dwarf share an orbit that gradually shrinks over hundreds of millions of years, the smaller helium white dwarf can eventually be dismantled by the gravity of its heavier partner, its helium bleeding onto the carbon-oxygen surface in a slow, steady stream, or in some scenarios, in a much more violent tidal disruption. Either way, the result is the same. Helium is delivered from one dead star to another, and the receiving white dwarf gains a thin outer layer of fresh fuel. There is also a third possibility, one where the companion is a more ordinary star that has evolved off the main sequence and swelled into a giant, and its outer atmosphere has been stripped of its lightest gases through complex previous interactions, leaving behind material that is unusually rich in helium. In this case, the companion is still an active star, still fusing internally, but its outer envelope has become helium-heavy through the accidents of binary evolution. As this giant swells and its outer layers loosen, that helium-heavy envelope can spill across the gap between the two stars and land on the white dwarf. The mechanism by which this transfer actually happens is worth understanding because it is beautiful in a strange way. Any two objects orbiting each other have a specific gravitational geometry between them, and inside that geometry there are regions called Roche lobes, which are essentially the volumes of space each star can gravitationally claim as its own. As long as a star stays inside its own Roche lobe, it holds onto its material. Its outer atmosphere belongs to it. But if the star swells, or if the orbit shrinks, and the star's surface reaches the edge of its Roche lobe, something remarkable happens at that boundary. There is a single point, a specific spot in space between the two stars, where the gravity of one and the gravity of the other exactly balance. It is called the inner Lagrangian point, and any material that reaches that point stops belonging to either star. It becomes contested territory, and gravity, being what it is, tips it. The material starts falling toward whichever star is on the other side. For a helium-donating companion in a close orbit with a white dwarf, this is exactly what happens. The companion swells, or its orbit tightens, its outer surface just barely reaches the inner Lagrangian point, and helium-rich material starts trickling across that boundary. It does not fall straight onto the white dwarf, because the whole system is spinning. The material has angular momentum, so instead of dropping in a clean line, it spirals inward, forming a thin disk of hot glowing gas around the white dwarf, called an accretion disk. Friction inside that disk slowly drags the material inward, spiraling it down through tighter and tighter orbits until eventually the innermost gas actually reaches the surface of the white dwarf itself and lands there. That accretion disk deserves a moment of attention because it is not a passive channel. It is a small, hot, complicated object in its own right, and its physics matters for how quickly and how steadily helium can be delivered. The disk is essentially a flat spinning pancake of gas, thin in the vertical direction, wide in the horizontal one, orbiting the white dwarf in nearly circular tracks. Gas in the outer parts of the disk moves relatively slowly. Gas in the inner parts, closer to the white dwarf, moves extremely fast, at speeds that can approach a substantial fraction of the escape velocity from the surface. And because gas at different radii in the disk is orbiting at different speeds, adjacent layers of the disk are constantly sliding against each other. That sliding produces friction, not the kind of friction you feel when you rub your hands together, but a more subtle, magnetic and turbulent kind of friction that transfers angular momentum outward and lets the inner material fall further inward, slowly, gradually, layer by layer, atom by atom. The disk feeds itself into the star. By the time material has spiraled all the way down through the disk and finally reaches the innermost edge, it is moving at astonishing speeds. It slams into the surface of the white dwarf, or more precisely, into a thin boundary layer just above the surface, where it decelerates from orbital velocity to something close to the white dwarf's own rotation rate. That deceleration releases an enormous amount of kinetic energy as heat and radiation. The boundary layer glows brightly in ultraviolet and even in X-rays, hot enough that many accreting white dwarf systems are among the brightest X-ray sources in nearby galaxies. The material that lands on the white dwarf, having traveled through this entire disk system, is what accumulates into the helium shell, but the delivery is not perfectly steady. The disk can go through periods of higher and lower activity, and these variations affect how quickly the helium shell grows. There is another subtlety here that is worth understanding, and it concerns the companion's own evolution during this long period of donation. The companion is not a static object. It is a star, still living, still burning its own fuel, still evolving through its own life stages. Over the hundreds of thousands or millions of years that it is donating material to the white dwarf, the companion itself may be gradually changing. If it is a helium star, it may be slowly burning through its own helium and evolving toward the end of its own life. If it is an evolved giant, it may be swelling further, or losing its outer layers entirely, or approaching its own eventual death. The rate at which material is transferred to the white dwarf can change as the companion evolves. Sometimes the transfer speeds up, sometimes it slows down, sometimes it stops entirely if the companion contracts back inside its Roche lobe or exhausts the material that had been available at the surface. This means that the helium shell on the white dwarf is not built at a single steady rate. It is built in fits and starts, with periods of faster growth and periods of near stagnation, all determined by what is happening on the far side of the binary orbit. And through all of this, the shell itself is aging. The oldest helium at the bottom of the shell has been sitting there under enormous pressure for as long as the shell has existed. It has been slowly warming, slowly compressing, slowly approaching the ignition conditions from below. The freshest helium at the top of the shell has just arrived and is still relatively cool. The whole shell has a structure, a stratification that reflects its own history of assembly. And this stratification is important because when ignition finally comes, it does not come to the shell as a whole. It comes specifically to the base, to the oldest, deepest, most compressed material, the helium that has been waiting the longest. And when that material finally reaches its own ignition point, it does so not because anything sudden has happened, but because a long, slow, unbroken process of accumulation and compression has quietly reached the threshold that had always been implicit in the physics from the very beginning of the transfer. The star was assembling its own trigger, one thin layer at a time, throughout the entire relationship with its companion. And now, that trigger is ready. Not all binary systems that produce double detonations necessarily go through this disk-mediated accretion. Some of the models involving a helium-white dwarf companion involve much more dramatic mass transfer, where the entire smaller white dwarf is disrupted and its material dumps onto the primary in a single catastrophic event or in the final stages of a merger. But the basic idea is preserved across all these variations. Helium arrives at the surface of the carbon-oxygen white dwarf. It does not have to arrive all at once. In many of the more traditional models, it arrives slowly, gently, over hundreds of thousands or millions of years, laid down in an ever-thickening layer. And now, here is where the physics starts to become interesting, because this incoming helium doesn't simply disappear into the white dwarf. It cannot mix into the deep interior in any quick or easy way. The white dwarf is a highly stratified object. It has structure. The heavier carbon and oxygen that make up its bulk sit deeper. The lighter helium sits on top, so the incoming helium accumulates. It piles up. It forms a distinct outer envelope, thin at first, then thicker, gradually building into a shell of pure or nearly pure helium wrapped around the entire dead star. Picture a sphere of degenerate carbon and oxygen, roughly the size of Earth, wrapped in a thin, dense skin of helium, delivered from a companion over 1 million years. That skin, that shell of accumulated helium, is where our story is about to turn violent. Because the helium at the top of the shell, the part closest to the companion, freshly arrived, is under relatively little pressure. But the helium at the very bottom of the shell, right where it presses against the carbon-oxygen surface of the white dwarf beneath, is being crushed. The full weight of the shell above it, plus the crushing gravity of the white dwarf itself, is squeezing that bottom layer with enormous force, and squeezing gas raises its temperature and raises its density and pushes it toward exactly the conditions where nuclear fusion becomes possible. Now, helium fusion in normal, non-degenerate conditions requires very high temperatures, around 100 million degrees, to proceed at any meaningful rate. That is the temperature at which 3 helium nuclei can collide and momentarily stick together to form carbon, in a process called the triple alpha reaction. In an ordinary star, this reaction is well behaved. It happens in the core of a red giant, and it is regulated by the same negative feedback we described earlier. If the fusion accelerates, the core expands, which cools the material, which slows the fusion back down. The star stays stable, but at the base of an accumulated helium shell on a white dwarf, the conditions are not ordinary. The helium there is being compressed to densities that are on the edge of becoming degenerate, or in some models, are fully degenerate. And that means when the temperature at the base of the shell climbs high enough to start helium fusion, the ordinary feedback loop is either weakened or gone entirely. The runaway physics we described earlier applies here in miniature. The helium shell is a smaller scale bomb sitting on top of a larger one, and once its base ignites, the burning accelerates with nothing to check it. But the runaway does not necessarily begin everywhere at once. This is a subtle point, and it matters, so let me linger on it. When the base of the helium shell finally reaches the temperature at which fusion starts to become significant, it does not do so uniformly across the entire spherical surface at exactly the same instant. Small differences in temperature, in density, in composition, in convective motions inside the shell all mean that some patches of the base reach the critical threshold slightly before others. Ignition begins somewhere, in a specific region, in a specific spot, and from that spot the burning has to spread outward through the rest of the shell. This is where three-dimensional geometry comes into the story in a way that is genuinely difficult to model and still an active area of research. In the simplest cartoon version of the mechanism, ignition begins at a single hotspot at the base of the shell, and a burning front then propagates around the star. But whether that front spreads as a slow deflagration or accelerates into a detonation depends on the local conditions in the shell in ways that computer simulations are still working through. It depends on the thickness of the shell, the density gradient inside it, the exact temperature at the ignition point, whether there is any carbon mixed into the helium, and details of turbulence and mixing that are extraordinarily hard to capture even with the most sophisticated codes. For the double detonation mechanism we are tracing tonight, the crucial requirement is that the initial helium burning must, at some point, transition into a genuine detonation. It must become a shock-driven, supersonic runaway that sweeps around the star. If it stays as a slower deflagration, it may still produce dramatic effects, and there are related models where a slow helium flare on a white dwarf produces a bright transient event that is much fainter than a supernova and leaves the star intact. But those are different outcomes. For the full double detonation story, the outer detonation is essential. So we have to trust, for the sake of this narrative, that the physical conditions in the accumulated helium shell can, and in at least some fraction of these binary systems apparently do, produce that transition from ordinary helium burning to a full-blown detonation. Once that transition happens, everything changes on timescales that are almost impossible to visualize. A detonation front in the helium shell moves at speeds of many thousands of kilometers per second, a small but real fraction of the speed of light itself. The entire circumference of the white dwarf is only about 40,000 kilometers or so, tiny by cosmic standards. And a supersonic burning front locked to a shockwave can race around that entire circumference in seconds, maybe less. Some models suggest the whole outer shell can be enveloped in detonation on a timescale short enough that, from the perspective of any observer watching the star, the surface simply lights up all at once in a blinding thermonuclear flash. Let me try to paint what is actually happening on the surface during this outer detonation, because it is worth appreciating. The helium in the shell is not just being burned uniformly, it is being consumed by a shock wave that compresses the fuel to enormous densities in the instant before ignition. The nuclear reactions that follow are not limited to the simple triple alpha process. Once the shock has raised the temperature high enough, other reactions become possible as well. Helium nuclei can combine with the freshly formed carbon to make oxygen. They can combine with oxygen to make neon. They can build heavier and heavier elements in a chain of alpha capture reactions that can, if conditions are right, reach all the way up into the iron peak of the periodic table. Nickel-56, one of the most important products of thermonuclear supernovae, can be produced in this outer burning as well as in the deeper detonation that follows. This is important because it means the surface detonation on its own would leave a distinctive signature. The outer layers of the exploding star, the material that gets thrown outward at the highest velocities and reaches the observer first, would be enriched with iron group elements from the helium detonation. And this is one of the historical problems with double detonation models. In some of the older versions, where the helium shell was assumed to be quite thick, the amount of iron group material produced in the outer detonation was so large that it should have produced spectral features in the resulting supernova that were not observed in most real Type Ia events. The colours would be wrong. The absorption lines would be wrong. The early light curve would show the signatures of freshly synthesized radioactive material in the outer layers in ways that would stick out clearly to modern instruments. This is why more recent theoretical work has increasingly focused on thin helium shells rather than thick ones. If the accumulated helium shell is relatively thin at the moment of ignition, then the total amount of iron group material produced in the outer detonation is small enough that it does not leave a strong, obviously anomalous fingerprint on the resulting supernova. The explosion looks more like a normal Type Ia supernova, and the double detonation model can therefore explain a broader range of observed events. There is also active work on shells that contain some contamination of carbon or other elements mixed in with the helium, which changes the burning products and can make the outer detonation produce different, less problematic elements. But no matter what the exact composition of the shell is, no matter how thick or thin it is, no matter what the exact ignition geometry looks like in 3 dimensions, the outer detonation, once it takes hold, does something crucial for the rest of the story. It does not just burn the helium, it creates a shock wave, a pressure wave, a wall of compression that races around the star along with the burning front, and, more importantly for what happens next, punches downward as well as sideways. Because remember, the helium shell is not floating in a vacuum. It is sitting on top of the carbon-oxygen surface of the white dwarf below. And when a detonation front sweeps through the shell, the shock wave associated with it does not just move parallel to the surface. Part of that shock is directed downward into the white dwarf beneath. The outer detonation pushes on the underlying material. It slams into the interface between the helium shell and the carbon-oxygen core with an incredible amount of energy. And that downward push is what carries the story inward, into the deeper layers of the star. Now, the amount of energy released by the helium detonation alone is significant, but it is not by itself enough to unbind the entire white dwarf. If all that happened was the surface detonation, without any further consequences, the resulting explosion would be dramatic. It would produce a burst of light, it would eject material at high speeds, it might even destroy the outer shell entirely and leave behind a partially intact white dwarf with its surface completely resurfaced. But it would not be a full supernova. The mass and energy involved are simply not enough. The bulk of the star, the carbon-oxygen core beneath the shell, would remain gravitationally bound and would ride out the surface explosion largely intact. So if that were all that happened, the double detonation mechanism would not really deserve the name. It would just be an outer detonation, one detonation, on a star that survives. To get the second detonation, to trigger the destruction of the core, you need something more. You need the shock wave from the surface detonation to reach into the deep interior of the white dwarf and do something to the carbon and oxygen there. Something extreme enough to ignite fuel that, up to this moment, has been sitting quietly in degenerate equilibrium, unable to ignite itself. And here we run into a genuinely subtle physical question, one that different research groups have modelled in different ways over the last several decades. The question is, exactly how does the outer detonation reach the core? By what geometry? By what path? By what compression? Does the surface explosion get down inside the star deeply enough to trigger the second ignition? There are several leading possibilities, and it is worth briefly mentioning them because tonight's story does not depend on any single one being definitively correct. The mechanism as a whole is real, but the specific ignition geometry of the second detonation is still an area of active research. One possibility is that the shock wave from the outer detonation converges near the center of the white dwarf. The idea here is that as the shock propagates inward from the surface, it wraps around the star and eventually meets itself at some point in the deep interior. In 3 dimensions, when a shock wave sweeping across a spherical surface meets itself on the far side, the point of convergence can produce extremely high densities and temperatures for a brief moment, essentially creating a hot spot where the incoming pressure focuses. If that convergence point lies deep enough in the carbon-oxygen material, and if the resulting conditions are extreme enough, then a fresh detonation could ignite there. This is the shock convergence pathway, and it has been explored extensively in numerical simulations. Another possibility is what is sometimes called the edge-lit detonation. In this picture, the second detonation ignites not deep in the interior, but right at the boundary between the helium shell and the carbon-oxygen core, driven directly by the enormous pressure the outer detonation applies at that interface. The idea here is that the shock does not need to travel all the way through the star to find a convergence point. It ignites the carbon almost immediately, at the point where the outer burning is pressing down hardest on the fuel below. This pathway leads to a slightly different geometry for the resulting explosion, with the core detonation beginning near the outer edge of the core rather than deep inside it. There are still other proposed variations, involving off-center ignition points, involving turbulence and mixing effects, involving specific properties of the helium core interface, and each of them predicts slightly different observational signatures. But the essential structure is the same. The outer detonation delivers a violent, focused push into the carbon-oxygen core. Somewhere in that core, a small region reaches the conditions required for carbon ignition. And once that region ignites, once carbon fusion begins in degenerate matter, the second runaway starts, and this one is the one that ends the star. But I am running ahead again. We have not yet fully appreciated the surface detonation for what it is. This astonishing event where a thin skin of stolen fuel, accumulated in silence for 1 million years or more, finally reaches the moment when the base of the shell hits ignition conditions and a burning front races around the surface of a dead star at supersonic speeds, wrapping the entire white dwarf in a flash of thermonuclear light that lasts only seconds and yet transforms the entire outer skin of the object into hot, radioactive ash. This surface flash is, in a very real sense, the trigger the white dwarf could never provide for itself. All those millions of years of quiet cooling, all those slow trickles of helium from the companion, all that gradual accumulation, layer by layer, of a thin outer shell of fuel, all of it building imperceptibly toward this single moment, the moment when the base of the shell finally reaches the critical temperature, when the runaway ignites, when the burning front races out from its starting point, and when, within seconds, the entire outer surface of the star is engaged in a thermonuclear reaction that generates a shock wave capable of reaching into the interior and doing to the core what the core could never do to itself. The white dwarf could not ignite from within. It was, for all its concentrated mass and enormous gravity, a bomb without a fuse. And the companion, over 1 million years of patient, quiet donation, delivered exactly the fuse that was missing. It draped the dead star in a skin of helium, and it waited. And physics did the rest. The base of the shell compressed. The temperature climbed. Ignition began somewhere. A detonation formed. And the surface of the star exploded. Now the shockwave is racing not only around the surface, but inward, downward, into the carbon and oxygen that make up the bulk of the star, into the sleeping mass of fuel that has been waiting for the right conditions for its own detonation, waiting for something to reach in from outside and squeeze it hard enough, from directions it did not have access to on its own to trigger the deeper explosion. The outer detonation is not the end. It is not the destruction of the white dwarf. It is only the first act. It is what happens when the fuse burns. What comes next is what happens when the payload of a stellar-scale bomb, ignited by the shockwave of its own burning surface, finally goes off. And to understand that, we have to follow the shockwave down into the dense, degenerate heart of the star, into the point of convergence, or into the interface layer where the second detonation begins, into the moment when the carbon itself finally lights. The shockwave has just been born. The outer helium detonation has swept around the entire circumference of the white dwarf in a flash of thermonuclear fire, and the surface is now enveloped in burning debris. But the energy released was not, on its own, enough to destroy the star. The deep interior, the degenerate carbon and oxygen making up the bulk of the object, is still there. Still bound. But that surface detonation did not just burn helium. It generated a shockwave. And that shockwave is now doing something extraordinary. It is falling inward. To understand what is about to happen, you have to picture the geometry very carefully. The white dwarf is a nearly perfect sphere. On its surface, at the base of the helium shell, a detonation has just swept around the entire circumference. And the shock associated with that detonation was not confined to the shell itself. Part of it, a substantial part, is being driven downward, into the carbon and oxygen beneath, into the dense heart of the star. Now, think about what a shockwave does in a spherical geometry. If you push inward on the surface of a sphere from every direction at the same time, if the entire outer boundary of the sphere is compressed inward simultaneously, then all of that inward moving energy has to go somewhere. It cannot spread outward because the outer edge is doing the pushing. It cannot dissipate quickly because degenerate matter is not particularly good at absorbing shock energy. So the shock waves converge. They move toward each other. They focus. And if the geometry is right, they meet at some point in the interior in a way that concentrates their combined energy into a tiny region of space. This is called shock convergence, and it is one of the leading pictures for how the second detonation begins. The idea is beautifully simple in principle. If you can compress the interior of a white dwarf from all directions at once, you can create a hot spot at the point where the compression peaks. And if that hotspot reaches conditions extreme enough to ignite carbon fusion, then the second runaway begins. But the reality inside the star is more complicated than this clean spherical picture suggests. Because the outer detonation, remember, did not begin uniformly across the entire surface. It began somewhere. It began at a hotspot in the base of the helium shell, and it spread from there. So the shock waves that are now traveling inward are not perfectly symmetric. They are shaped by where the surface detonation started, by how it propagated, by the three-dimensional structure of the shell above the star. This asymmetry matters because instead of all the shocks meeting exactly at the geometric center of the white dwarf, they meet somewhere else. Somewhere off-center. Somewhere determined by the specific way the outer detonation unfolded. And the exact location of that convergence point in three-dimensional simulations turns out to be a critical detail. Different starting conditions in the helium shell produce different convergence geometries, and different convergence geometries produce different outcomes for whether the second detonation successfully ignites. Let me try to describe what is happening at this convergence point in physical terms. As the shocks from different regions of the surface meet, they compress the carbon and oxygen material there beyond what any single shock could do on its own. The density spikes, the temperature spikes, and in a region that might be no larger than a fraction of the star's total volume, the conditions momentarily reach values that no other part of the interior has experienced. Temperatures approaching or exceeding 1 billion degrees, densities that push the material into a regime where carbon fusion becomes not just possible, but explosively fast. Let me linger on what shock convergence actually means, because it is worth appreciating as a physical effect in its own right. When two shock waves traveling through a medium collide head-on, or when multiple shocks arriving from different directions meet at a single point, the compression they produce is not simply additive, it is multiplicative. The material at the convergence point is compressed by one shock, and while it is still under that compression, another shock arrives and compresses it further, and another. And the resulting state of the material at the point of convergence is far more extreme than any single shock could have produced acting alone. The same underlying principle applied to supersonic shock waves in extraordinarily dense matter produces conditions that are almost unimaginable. The material at the convergence point is briefly compressed to densities several times higher than the ambient density of the white dwarf itself, which was already among the densest matter in the universe outside of neutron stars and black holes. And this happens in an extremely small region. The convergence point in most simulations is not a large volume. It is a spot perhaps only a few hundred kilometers across, deep inside a star that is itself thousands of kilometers across. Most of the interior of the white dwarf, in the moments during and after the convergence, is not at these extreme conditions. Only the small region at the focus is. But that small region is exactly where the physics required for carbon ignition can be reached, and it is exactly where the second detonation, therefore, has its best chance of beginning. The timescales involved are almost impossibly short. From the moment the outer detonation first ignites at the base of the helium shell, to the moment the resulting shock wave has travelled inward and converged at some point in the deep interior, the total elapsed time is on the order of a fraction of a second. Perhaps a few tenths of a second at the outside. The white dwarf is not a large object, and shock waves in dense matter move fast. By any human standard, the two detonations are essentially instantaneous with each other. From the moment the second detonation ignites at the convergence point, the burning front races outward through the rest of the star at many thousands of kilometers per second, and the entire carbon-oxygen interior is consumed within seconds. The full sequence, from the first spark in the helium shell to the total destruction of the underlying star, unfolds in less time than it takes to say the word supernova out loud. And here is where the degeneracy of the material becomes the villain of the story again. The same physics that made the helium shell unstable now applies with even greater force to the carbon core. There is no thermostat. There is no expansion. The reactions release heat, and that heat has nowhere to go except into driving the next reactions faster still. And carbon fusion, like every other nuclear reaction, is exquisitely sensitive to temperature. A modest jump in temperature drives an enormous jump in reaction rate. That jump in reaction rate produces more heat. That heat drives the rate faster still, and within a fraction of a second you have a runaway. A second runaway, a genuine detonation of the carbon and oxygen itself. This is the moment the white dwarf dies. But before we follow the second detonation outward, I want to pause and talk about the alternative ignition pathways, because the shock convergence picture is not the only one physicists have explored. It is one of the leading candidates, but the full landscape of double detonation models includes several variations. And it is worth being honest about the fact that different simulations, using different initial conditions and different numerical techniques, sometimes favor different pathways. One important alternative is the edge-lit detonation. In this picture, the second detonation does not need to wait for shock convergence in the deep interior. Instead, it ignites almost immediately at the boundary between the helium shell and the carbon-oxygen core, right where the outer detonation is pressing down hardest on the fuel below. The idea here is that the pressure of the surface detonation on the underlying material is so intense at the shell core interface that the carbon there is pushed into ignition conditions directly, without needing shocks to travel through the star and converge somewhere else. The edge-lit scenario produces a different geometry for the resulting explosion. Instead of the second detonation beginning at a small off-center point in the deep interior, it begins near the outer edge of the carbon-oxygen core and propagates inward from there, eventually consuming the entire core as it goes. The overall outcome is similar in the sense that the white dwarf is still destroyed, but the details of how the burning propagates through the star, and therefore the details of what the final explosion looks like from outside, are different. Another possibility involves ignition somewhere in between these two extremes. A location that is neither at the deep convergence point nor at the immediate shell core interface, but somewhere in the outer regions of the carbon-oxygen material, where the inward-moving shock has compressed and heated the fuel enough to trigger ignition without needing to travel all the way to the center. Some simulations produce ignition in exactly this intermediate region, and depending on the specific conditions, the resulting detonation can propagate either inward through the star or outward toward the surface, or in some cases in both directions from the ignition point. The honest answer is that we do not yet know with certainty which of these ignition geometries actually occurs in real double detonation events. It probably varies from system to system, depending on the mass of the white dwarf, the thickness of the helium shell, the exact composition of the shell, the temperature structure inside the star, and details of the surface detonation that are extraordinarily hard to model, even with the best current simulations. Different research groups have produced different answers over the years, and the field continues to evolve as computer models improve and as new observational data comes in. But the essential structure of the story is preserved across all these variations. The outer detonation drives a shock wave into the interior. That shock wave, either by converging in the deep interior, or by pressing directly on the shell core boundary, or by some combination of these effects, creates a small region somewhere inside the star where carbon fusion ignites, and that ignition in degenerate matter becomes a runaway. And the runaway becomes a full detonation, and the detonation sweeps outward through the rest of the star. So let me focus on that outward sweeping second detonation, because it is the event that actually destroys the white dwarf. It is the payload of the bomb. Everything before it, the accumulation of helium on the surface, the outer detonation, the inward moving shock, all of that was the trigger and the fuse. This is the explosion itself. Once carbon ignition begins in the interior of the white dwarf, the detonation front propagates outward through the carbon and oxygen material at supersonic speeds. Just like the outer detonation in the helium shell, this second detonation is a shock wave with a burning front locked to it. The shock compresses the fuel ahead of it. The compression triggers fusion. The fusion releases energy that helps drive the shock forward. The whole thing feeds on itself. Self-sustaining, unstoppable, consuming the fuel of the star at speeds close to a significant fraction of the speed of light. And the fuel it is consuming is enormous. Remember, the white dwarf holds roughly the mass of the Sun in a volume about the size of the Earth. That is a truly staggering amount of nuclear fuel packed into a tiny space. When carbon fuses to oxygen, oxygen fuses to neon, neon fuses to magnesium, and the chain of reactions climbs up the periodic table toward the iron peak, each step releasing energy. The total amount of energy liberated when a substantial fraction of the solar mass of carbon and oxygen is fused into heavier elements is genuinely difficult to visualize. It is comparable to all the energy the Sun will produce over billions of years of ordinary fusion. It is a burst of nuclear output that no ordinary stellar process can match on any short timescale, and it is all released in a matter of seconds. That energy has consequences. Specifically, it has one very important consequence. It exceeds the gravitational binding energy of the white dwarf. Let me explain what that means, because it is the key to understanding why the star does not survive this event. Every gravitationally bound object, every star, every planet, every rock, has what physicists call a gravitational binding energy. It is the amount of energy you would need to supply to the object to blow it apart against its own gravity, to unbind all the mass from itself and scatter it to infinity. For the Earth, the binding energy is enormous by everyday standards, but small by cosmic standards. For a star, it is much larger. For a white dwarf, it is larger still, because you have taken a stellar mass amount of material and compressed it to Earth-sized dimensions. And the tighter you pack mass together, the more energy you need to disperse it. But even the binding energy of a white dwarf, which is enormous, is not infinite. And when carbon detonation fuses roughly a solar mass of light nuclei into heavier ones, the total nuclear energy released in the process is greater than that binding energy, much greater. And what this means, in physical terms, is that after the detonation is finished, the star cannot possibly hold itself together anymore. The energy of the explosion is more than enough to fling every atom of the former white dwarf outward at speeds tens of thousands of kilometers per second, permanently escaping the object's own gravitational grip. The white dwarf is disrupted, not damaged, not partially destroyed, completely disrupted. Every gram of material that used to make up the star is now hot, expanding gas, moving outward into space. There is no remnant core. There is no leftover neutron star or black hole or anything else. Unlike the more famous type of supernova, the kind produced by the collapse of very massive stars, which leaves behind a compact object at the center. A successful double detonation of a white dwarf leaves behind nothing at all. The star is gone, every atom of it, redistributed across space in an expanding cloud that will eventually become the seed material for new stars and new worlds elsewhere in the galaxy. This is a truly remarkable thing to sit with for a moment. The object that existed just seconds ago, an Earth-sized ball holding a full solar mass of degenerate carbon and oxygen, exists no more. And it did not die because of some external catastrophe. It died because of a single thin layer of stolen fuel on its surface, which ignited, which sent a shock inward, which triggered a second ignition in its interior, which released enough nuclear energy to fling the entire star apart. All of it happened in seconds. All of it originated in the accumulation over 1 million years or more of a helium layer no thicker than a small fraction of the star's total mass. Now, let me address the timescales here. Because they matter, and because they are somewhat counterintuitive. From the outside, from the perspective of a distant observer, the two detonations are not seen as two separate events. They belong to a single supernova, one unfolding thermonuclear catastrophe, and they are separated by so little time that no telescope watching from across the galaxy could resolve them as distinct flashes. The outer detonation ignites. The shock races through the star. The second detonation ignites. The star disintegrates. And all of this takes place on timescales measured in seconds. Fractions of a second in some models, perhaps a few seconds in others. The exact delay depends sensitively on where the second detonation ignites, on the mass and structure of the white dwarf, on the details of the shock propagation, and on other factors. But the key point is that the delay is short, absurdly short. From any practical observational standpoint, the two detonations are simultaneous. They are one event. That is why the mechanism is called a double detonation rather than two separate supernovae. Both burnings belong to the same rapidly unfolding thermonuclear event, and the second one, the destructive one, is caused directly by the first. Now, why does this matter as a story? Why is the double detonation mechanism interesting to astronomers beyond the pure novelty of an outside-in ignition sequence? The answer has to do with a long-standing puzzle in astrophysics. Type Ia supernovae, which are the general class of thermonuclear supernovae that includes double detonation events, have historically been one of the most important tools for measuring distances in cosmology. They are what astronomers call standardizable candles, meaning that their intrinsic brightness can be calibrated in ways that let us use them as distance markers across billions of light years. The 1998 discovery of the accelerating expansion of the universe, which won the Nobel Prize in Physics in 2011, was based on measurements of type Ia supernovae. But there has always been a fundamental question about what these events actually are. What kind of star produces them? What is the exact progenitor system? For decades, the standard model was what is called the near Chandrasekhar single degenerate scenario. In this picture, a carbon-oxygen white dwarf slowly accretes hydrogen-rich material from a companion, gradually gaining mass, until it approaches the Chandrasekhar limit, which is roughly 1.4 times the mass of the Sun. At this point, the pressure at the center of the white dwarf becomes so extreme that carbon ignites in the deep core, triggering the runaway that destroys the star. In this scenario, the ignition is central. It begins at the center of the star and propagates outward, The Chandrasekhar limit is worth understanding here, because it plays an important role in the broader landscape of thermonuclear supernova models. The limit is a fundamental consequence of the physics of electron degeneracy pressure, discovered by the physicist Subrahmanyan Chandrasekhar in the 1930s. The basic idea is that as you add more and more mass to a white dwarf, the electrons inside get squeezed harder and harder, but the pressure they can provide is limited. At speeds approaching the speed of light, the electrons cannot push back any harder than they already are, no matter how much you compress them. And this means there is a maximum mass, roughly 1.4 times the mass of the Sun, beyond which electron degeneracy pressure simply cannot support the star against its own gravity. If a white dwarf grows past this limit, it must either collapse into a neutron star, or, if fusion ignites first, explode as a supernova. For a long time, the near Chandrasekhar model was the default picture for Type Ia supernovae, but it has always had problems. The rate of Type Ia supernovae observed in the universe is higher than the rate at which we would expect white dwarfs to grow to the Chandrasekhar limit through steady accretion. The observed diversity of Type Ia supernova brightnesses and spectra is difficult to explain if they all come from essentially identical events at the Chandrasekhar limit. And direct searches for the surviving companion stars that should exist after a near Chandrasekhar explosion have largely turned up empty, which is not what you would expect if this were the dominant channel. The Double-Detonation model offers a different picture, and one of its most attractive features is that it allows a white dwarf to explode below the Chandrasekhar limit. In fact, it does not require the white dwarf to be anywhere near that limit at all. A carbon-oxygen white dwarf with a mass of 1 solar mass, or 9/10 of a solar mass, or even less, can potentially explode as a Type Ia supernova through the double-detonation mechanism, provided it accumulates enough helium on its surface for the outer detonation to trigger the inner one. This dramatically expands the range of stars that can produce Type Ioic supernovae, and offers a natural explanation for why the observed rate of these events is as high as it is, without requiring every event to reach the Chandrasekhar limit. This is why the double detonation mechanism has attracted so much attention in recent decades. It is not just a theoretical curiosity. It is one of the leading candidates for explaining a significant fraction of the Type Ia supernovae we observe in the sky. And because Type Ia supernovae play such an important role in cosmology, understanding which of them come from which progenitor channel matters not just for stellar physics, but for our broader picture of how the universe evolves. But let me return to the mechanism itself, because I want to say something about how it is distinguished from other proposed pathways to thermonuclear stellar destruction. It is easy to get confused about the different kinds of events, so let me try to make the distinctions clear. A nova, in the technical sense, is what happens when a white dwarf accretes hydrogen from a companion and that hydrogen ignites on the surface in a fast but relatively contained burst. A nova is bright, sometimes dramatically so, and it can throw off some material into space. But it does not destroy the white dwarf. The star survives. It resumes accreting after the outburst, and eventually, it can produce another nova. There are white dwarfs known to have produced multiple novae over recorded human history. A nova is a surface event, and the underlying star is intact after it is over. A helium nova is similar in concept, but involves helium rather than hydrogen, If the helium accumulation on a white dwarf ignites, but the burning does not transition into a full detonation or does not send a shock strong enough to trigger the core, the result can be a bright, transient event that ejects some material but leaves the star intact. This is a helium nova, and it is a distinct outcome from a successful double detonation. A classical single central runaway, the near Chandrasekhar scenario I described a moment ago, involves ignition at the center of the star rather than on the surface. It is a thermonuclear supernova, and it destroys the white dwarf completely. But the ignition geometry is fundamentally different from the double detonation case. In the central scenario, the burning begins in the core and propagates outward. In the double detonation case, the first burning begins on the outside, and the second burning ignites in the interior only because of what happened on the outside first. The merger of two white dwarfs is another proposed pathway to type Oya supernovae, and it involves a completely different sequence of events. In this picture, two white dwarfs in a very close binary orbit spiral together over time due to gravitational wave emission, eventually merging in a violent event that either directly ignites carbon or produces a temporary object that ignites shortly after the merger. This is sometimes called the double degenerate scenario, and it is a live area of research, but it is distinct from the double detonation of a single white dwarf triggered by an accumulated helium shell. There is also a class of related events called dynamically driven double degenerate double detonations, which combine some features of both the merger scenario and the surface helium detonation scenario. In these models, a helium white dwarf and a carbon-oxygen white dwarf are locked in a very close orbit. During the final stages of their in-spiral, before a full merger, the smaller helium white dwarf begins to lose material onto the surface of the carbon-oxygen white dwarf in a very fast, very violent way. This material forms a helium layer on the surface, which then detonates, driving a shock into the interior in exactly the same way we have been describing. The core of the primary white dwarf then ignites via one of the same ignition pathways, and the star is destroyed. In this variant, the trigger is not a slow accumulation over a million years, but a dynamic interaction near the end of the binary's life. Type IAC supernovae are related events that appear to involve incomplete explosions, typically less bright than normal type YA events, possibly leaving behind a bound remnant. They are thought to involve different physics, possibly a deflagration that fails to transition into a detonation. The point of listing all these related events is not to overwhelm you with taxonomy, but to emphasize that the double detonation mechanism is a specific, distinct pathway with a specific, distinct signature. It is not the same as a nova, not the same as a central runaway, not the same as a merger, not the same as a type IAX event, though it belongs to the same broad family of thermonuclear stellar phenomena. What makes it unique, what gives it its name, is the two-stage structure of the ignition: outer first, then inner, surface first, then core, and the second stage, the inner detonation, is caused directly by the first, not by any independent process happening in the core on its own. Now, one might reasonably ask, if the second detonation is what destroys the star, why do we bother emphasizing the first detonation at all? Why not just call this the carbon detonation and be done with it? The answer is that the first detonation is what makes the whole event possible. Without the surface detonation, the carbon core would never ignite. It would sit quietly forever, a stable white dwarf, unchanged, it is only because the outer skin of helium was assembled by accretion from a companion, and only because that outer skin ignited, and only because the resulting shock reached the interior, that the second detonation can happen at all. The first detonation is the trigger. Without it, the payload never goes off. And that is why the story of the double detonation is, at its heart, the story of how a dead star that could not ignite itself was ignited from the outside, and how the outside ignition forced the interior to explode as well. The white dwarf, at this moment, is finished. The carbon detonation has swept through its interior, converting a substantial fraction of its mass into heavier elements and releasing enough energy to unbind the star from itself. What was once a stable, cool, ancient remnant is now an expanding cloud of hot, radioactive debris moving outward into space at thousands of kilometers per second. But the story is not over. The most spectacular observable consequences of the double detonation are only just beginning. The star has disintegrated, yes, but the energy released in the process is not simply going to disappear into empty space. It is going to power something visible, something bright, something that can be seen across billions of light years for weeks and months to come. And it is going to leave chemical fingerprints in the expanding debris, fingerprints that astronomers can, in principle, use to distinguish this pathway from all the other ways a star can die. And that is where we turn next, to the aftermath, to the light, to the ashes, and to the difficult, subtle, still unfolding question of how we tell, from billions of light years away, whether the supernova we just saw was caused by the specific outside-in sequence we've been tracing, or by one of the other pathways that can produce a similar kind of explosion. The white dwarf is gone. In the seconds before this moment, the stolen helium on its surface detonated. The resulting shock triggered a second detonation in the carbon-oxygen core, and the nuclear runaway released more energy than gravity could contain. Every gram of what used to be the star is now hot, expanding gas, hurled outward at tens of thousands of kilometers per second, permanently unbound. But the star has not yet become bright. That may surprise you. The peak visible light of a thermonuclear supernova, the point at which it briefly outshines an entire galaxy, does not come from the initial explosion itself. The energy released by the nuclear reactions is enormous, but most of it goes into simply flinging the star apart. Kinetic energy, motion. The debris moves outward at a substantial fraction of the speed of light. And for the first few days after the explosion, the expanding cloud is actually quite dense and quite opaque. Light generated inside it cannot easily escape. The photons bounce around, get absorbed, get re-emitted, and slowly diffuse outward through material that is expanding and thinning as they go. What produces the spectacular brightness we associate with the type I supernova, the brightness that lets us see these events from across the observable universe, is not the initial detonation at all. It is what comes next. It is the slow decay of the radioactive elements that were freshly made in the explosion. And the most important of those elements, by far, is nickel-56. Nickel-56 is one of the most remarkable substances in stellar physics. It is an isotope of nickel that has an unusual property. Under everyday laboratory conditions on Earth, nickel-56 is radioactively unstable. It does not last. It decays with a half-life of about 6 days into cobalt-56. And cobalt-56 is itself unstable, decaying with a half-life of about 77 days into iron-56, which is finally stable and lasts forever. Now, Why does this matter? Because in the carbon detonation that has just destroyed the white dwarf, the nuclear reactions in the deepest and densest regions of the star do not stop at carbon and oxygen fusion. The temperatures and densities in the burning are so extreme that the reactions climb all the way up the periodic table toward the Iron Peak. And along the way, an enormous amount of nickel-56 is produced. In a typical successful double-detonation supernova, or indeed in most Type Ia supernovae from other mechanisms, roughly half of a solar mass of nickel-56 is created. This freshly synthesized radioactive nickel is now embedded in the expanding cloud of debris. Over the following days and weeks, that nickel-56 decays into cobalt-56, and then, more slowly, into iron-56. Each decay releases a gamma-ray photon of very specific energy, along with some other particles. Those gamma rays cannot easily escape from the still dense expanding cloud, so they get absorbed by the surrounding material, transferring their energy into heat. The debris cloud heats up, and a hot, expanding cloud radiates. It glows. This is what powers the visible light curve of a Type Ia supernova. Not the original explosion, but the slow, steady release of energy from the decay of nickel-56 and cobalt-56 embedded in the debris. The supernova brightens over about 3 weeks as the cloud expands and becomes optically thin enough for the light to escape. Reaches a peak brightness at which it can outshine an entire galaxy, and then fades over months as the radioactive material is used up, and as the cloud continues to expand and thin. For observers on Earth, or on any planet with telescopes, the light curve is what we see. We do not see the outer detonation. We do not see the shock wave. We do not see the inner detonation. All of that happened in seconds, hidden inside a rapidly expanding cloud of debris that was still, in those first moments, too dense for the internal drama to be visible from the outside. What we see is the aftermath, the nickel-56 decaying in the ashes, the gamma rays being absorbed by the ejector, the heat being converted to visible light, the visible light escaping and traveling to our telescopes across space. But hidden in the details of that visible light is a wealth of information. And that information, potentially, is what could someday let astronomers say definitively that a particular observed supernova was produced by the double-detonation mechanism specifically, rather than by any of the other pathways we discussed earlier. The question of how to tell these events apart from the light alone is one of the most active areas of current research in stellar astrophysics. Let me try to explain what the fingerprints might look like. The outer detonation, the one that swept around the helium shell at the very start of the sequence, produced its own set of nuclear ashes. Depending on the composition and thickness of the helium shell, and depending on the details of the burning, this outer detonation can create a variety of elements. It certainly produces some carbon and oxygen from the triple alpha process, but it also produces heavier elements from a chain of alpha capture reactions. Silicon, sulfur, calcium, titanium, chromium, and even some iron group elements, including a modest amount of nickel-56, can be synthesized in the helium shell burning. Now here's the key point. Those outer detonation products end up in the outer layers of the exploding cloud. Because they were made on the surface of the white dwarf, near the initial helium shell, they get carried outward at the highest velocities during the expansion. They are the first material any observer sees. They dominate the earliest phases of the light curve and the spectrum, and they can, in principle, leave distinctive signatures that would not appear in a normal Type Ia supernova produced by, say, a central runaway inside a Chandrasekhar mass white dwarf. The problem is that the exact signature depends sensitively on how much material was in the helium shell at the moment of ignition, and on the composition of that shell. Older double-detonation models tended to assume relatively thick helium shells, on the order of 1/10 of a solar mass or more. Those models predicted large amounts of ion group material in the outer ejecta, producing spectral features that were reddish and had strong absorption lines in specific parts of the ultraviolet and optical. When astronomers compared these predictions to actual observed Type Ia supernovae, the match was not good. Real Type Ia events did not, for the most part, show the strong outer ion group signatures that thick shell models predicted. This was, for a long time, considered one of the biggest problems for the double-detonation model. It seemed like the mechanism should produce supernovae that look distinctly different from the majority of Type Ia events we actually observed. And that was uncomfortable, because the theoretical attractions of the mechanism were strong. But over the last decade or so, a new generation of models has begun to explore thinner helium shells, and the outlook has changed considerably. If the helium shell at the moment of ignition is much thinner than the older models assumed, on the order of 1/100th of a solar mass or even less, then the total amount of outer detonation ashes is small enough that the resulting spectral features become subtle. Instead of dominating the spectrum, they become mild perturbations, and in some of these thin shell models, the predicted supernova signatures start to look quite similar to observed Type Ia events. Not identical, but close enough that the mechanism can no longer be ruled out on spectral grounds. There are also models that explore the possibility of the helium shell being contaminated with carbon or other elements, either because of mixing between the shell and the underlying core, or because of the specific way the shell was assembled from the companion. Contaminated shells produce different burning products, and in some cases they produce ashes that look even more similar to standard Type Ia signatures. The details are subtle and the modelling is genuinely difficult, but the overall trajectory of the field has been toward models where thin, possibly contaminated helium shells produce supernovae that are hard to distinguish from other Type Ia events, at least in bulk, light curve, and spectral properties, where the double-detonation model might still show its hand, according to some current theoretical work, is in specific detailed features. One promising area is the early time behavior of the light curve in the first day or two after the explosion. If a significant amount of radioactive material was produced in the outer detonation, and that material sits in the outer layers of the debris cloud, it can produce a brief early flash or excess of light before the main light curve rises. This early flash would come from the outer radioactive material heating the outer ejecta before the main body of the supernova becomes visible. Some observed Type Ia supernovae have shown early excess light that could potentially be explained this way, though other explanations, such as interactions with a companion star, are also possible for the same feature. Disentangling these possibilities is genuinely difficult. Another potential signature is in the velocity structure of the ejecta. Because the outer detonation produces material moving very fast, at velocities well above what the core detonation alone would produce, high velocity features in the spectrum of certain elements could indicate the presence of an outer helium detonation. Silicon, calcium, and other intermediate mass elements sometimes show very high velocity absorption features, in type Ia spectra. And some researchers have argued that these features could be signatures of double detonation events. But again, alternative explanations exist, and the interpretation is not yet settled. The overall observational picture, honestly, is that no single spectral or light curve feature has yet been identified that uniquely and unambiguously proves that a particular observed supernova was produced by the double detonation mechanism. There are suggestive features, promising candidates, and specific events that appear consistent with double detonation predictions, but the field has not yet reached a consensus on any definitive smoking gun. This is not because the mechanism is wrong, but because the observational signatures of different type Ya progenitor channels are often quite similar to each other, and the differences that do exist tend to be subtle enough that they can be mimicked by other physical effects or hidden by the diversity of properties across different white dwarfs. And this brings me to a subtle but important point. The observed appearance of a double detonation supernova depends on many factors that vary from event to event. The mass of the underlying white dwarf, the thickness of the helium shell at ignition, the composition of that shell, the location where the second detonation began, whether at the deep convergence point or at the shell core interface or somewhere in between, the three-dimensional structure of the burning, the viewing angle from which we observe the event. That last factor, the viewing angle, deserves special attention because it is easy to overlook. If the ignition of the outer detonation begins at a specific hotspot on the surface of the white dwarf, then the resulting burning is not necessarily perfectly symmetric. Some directions might have more nucleosynthetic products than others. The debris cloud might expand faster in some directions than others. And so an observer looking at the supernova from one angle might see slightly different light curve and spectral features than an observer looking from a different angle at the same event. This asymmetry adds another layer of complexity to the interpretation of individual events, and it may explain some of the diversity in observed type Ya properties. Given how difficult it is to identify a specific supernova as a double detonation event from its light and spectrum alone, another line of evidence becomes potentially important. That is, finding the surviving companion star after the explosion. Remember, the double detonation mechanism requires a binary system. Something had to donate the helium that accumulated on the white dwarf's surface. And after the white dwarf is destroyed, the companion, if it still exists, should still be there. It should still be flying through space, though without its former partner, it is no longer in orbit around anything. It should be moving at whatever velocity it had at the moment the primary detonated. Now, this is an interesting observational test. In principle, if you can identify the location of a past supernova, you can look for a star at that location moving at high velocity relative to the surrounding stars. Such a star, sometimes called a runaway star or a hypervelocity star, could be the surviving companion of the exploded white dwarf, kicked into rapid motion by the sudden removal of its partner and any explosive effects of the supernova on it directly. For nearby historical supernovae, this search is possible in principle. Astronomers have looked for surviving companions near the remnants of the Tycho supernova of 1572 and the Kepler supernova of 1604, both thought to be type Ia events. If either was a double detonation, a fast-moving companion should still be nearby. If either was a double detonation, a fast-moving companion should still be nearby. The results of these searches have been mixed and, honestly, a bit puzzling. Some candidates have been proposed. Some have been ruled out. In some cases, stars have been identified that appear to be moving fast enough to be plausible surviving companions, but their properties are unusual enough that their exact origin remains uncertain. For the Tycho supernova in particular, there has been a long debate about whether any of the observed nearby stars is truly the former companion, or whether the absence of an obvious companion actually argues against the single degenerate scenario, and in favour of a double degenerate scenario, in which both stars were white dwarfs, and one was destroyed, while the other perhaps also did not survive. Different double detonation models predict different kinds of surviving companions. If the donor was a helium star, then a hot blue low-mass star should still be there. If the donor was another white dwarf, then either another white dwarf should still be nearby, or in the dynamically driven double degenerate scenario, both stars might have been destroyed and no companion at all should remain. If the donor was a more ordinary evolved star, then some kind of stripped stellar remnant should still be observable. The lack of a clear consensus on what has actually been found for any specific supernova remnant reflects, in part, the fact that different mechanisms produce different expectations, and untangling which mechanism was responsible for which specific event is genuinely hard. There is also the possibility of looking at supernova remnants themselves, at the expanding shells of debris left behind by past supernovae, to look for chemical signatures of the explosion. If the double detonation mechanism produces a specific pattern of elements, particularly in the outer layers of the ejector, then careful observations of remnants might reveal that pattern in the composition of the shocked debris. This kind of work is being done for several nearby remnants, and it is one of the more promising avenues for eventually identifying past events as having been produced by specific progenitor channels. But identifying the exact pathway that produced any specific past supernova, especially one that occurred hundreds or thousands of years ago, and whose remnant has now expanded and mixed with surrounding interstellar gas, is genuinely difficult. The chemical fingerprints get diluted. The velocity information gets scrambled. Any evidence of asymmetry from the explosion gets obscured. And so, even for the closest and best studied cases, the case for any particular explosion mechanism remains circumstantial rather than conclusive. This uncertainty extends to the broader question of what fraction of all type Ia supernovae are actually produced by the double detonation mechanism. The honest answer is that we do not know. It could be a small minority. It could be the dominant channel. It could vary depending on the properties of the galaxy in which the events occur, or on the age of the stellar population, or on other factors we do not fully understand yet. Different theoretical arguments have supported different fractions, and the observational tests are not yet definitive. What is clear, though, is that type Ia supernovae as a class are almost certainly not all produced by a single mechanism. There is too much diversity in the observed events, in their light curves, in their spectra, in the environments in which they occur, to be fully explained by any single scenario. It is much more likely that multiple pathways contribute, and that the double detonation mechanism, whatever fraction it represents, is one channel among several that together produce the full population of these events. This is important to keep in mind whenever anyone talks about type Ia supernovae as if they were all fundamentally identical. They are not. And the details of the differences between them, though subtle, matter both for stellar physics and for the cosmological applications of these events. Speaking of cosmology, let me briefly return to why any of this matters beyond the intrinsic scientific interest of understanding stellar death. Type Ia supernovae are used as distance markers across the observable universe. Their peak brightness can be calibrated in ways that let astronomers determine how far away they are. And by measuring their distances at different points in cosmic history, we can trace how the expansion of the universe has changed over time. This is how we discovered that the universe's expansion is accelerating, driven by what we call dark energy, and it is how we continue to constrain the properties of dark energy today. This application depends on assumptions about the underlying uniformity of the events. If different type Ia supernovae come from different progenitor systems producing subtly different explosions, the calibration becomes more complicated. Understanding which channels produce which kinds of events is therefore not just a question of stellar astrophysics, but of precision cosmology as well. This is one of the reasons why so much effort continues to go into refining our understanding of the double-detonation mechanism and other type Ia pathways. It is not just about explaining a single class of stellar death. It is about ensuring that our tools for measuring the universe at the largest scales are as reliable as we think they are. If type Ia supernovae come from multiple mechanisms with subtly different properties, then untangling those mechanisms and correcting for their differences becomes essential for pushing cosmological measurements to higher and higher precision. Now, let me acknowledge what remains genuinely uncertain about the mechanism itself, because I have been trying to present the physics in a clear narrative, but honesty requires me to name the open questions as well. We do not fully understand how helium ignites in accumulated shells on white dwarf surfaces. The transition from stable or quiescent burning to a full detonation depends on details of the local physics, the composition, the temperature structure, and the three-dimensional geometry, and these details are extraordinarily hard to model precisely. Different research groups produce different answers depending on their numerical techniques, and there's not yet full consensus on exactly what conditions are required for a successful outer detonation. We do not know exactly how thin the helium shell can be while still successfully triggering the outer detonation. There is a lower limit somewhere, below which the accumulated helium is not sufficient to detonate. Where exactly that limit lies is an active area of research, and the answer matters for how frequent double detonation events should be in the universe. We do not know with certainty that the outer detonation always successfully triggers the inner one. There may be conditions under which the surface burning occurs, but the shock is too weak, or the geometry is wrong, and the core does not ignite. Such a failed double detonation would produce a very different kind of transient. Not a supernova, but a fainter, faster event in which only the helium shell burns while the underlying white dwarf survives. Whether such events actually occur and how common they are is not fully settled. We do not know how frequently the required binary systems form. Whether the white dwarf accretes helium from a helium star, from another white dwarf, or from an evolved companion with a helium-rich envelope. The specific binary evolutionary pathways that lead to double detonation configurations are complex and depend on many uncertain parameters. Different population synthesis studies produce different predictions for the rates of these systems, and reconciling those predictions with the observed rate of type Ia supernovae is an ongoing challenge, and we do not know for any specific observed type Ia supernova whether it was produced by the double detonation mechanism as opposed to one of the other proposed channels. As I discussed earlier, The observational signatures of different mechanisms tend to be subtle and overlapping, and there is not yet a clean way to identify individual events with certainty. All of these uncertainties are what make the field so active. The double-detonation mechanism is not a settled story. It is a working framework, with many pieces well understood and many others still being investigated. But the essential physics, the accumulation of helium from a companion, the ignition and detonation of the helium shell, the propagation of the shock into the carbon-oxygen core, and the second detonation that destroys the white dwarf, all of that is on solid theoretical ground. Whether it happens in exactly the way any specific model predicts, and how often it happens compared to other pathways, are the questions still being worked out. And now, at the end of this story, I want to return to the strange and beautiful thing that started us off. The idea that a dead star, an ember with no fuel it can access, no way to ignite itself, no source of energy left in its interior, can nonetheless explode. And that the explosion, when it comes, does not begin where you would expect it to begin. If you had asked, before the details of this mechanism were worked out, how a white dwarf could ever explode, you would have naturally guessed that the ignition must happen somewhere in the deep interior. That is where the fuel is thickest. That is where the density is highest. That is where the temperatures, though not yet enough for ignition on their own, are closest to what would be needed. Any reasonable intuition about how a bomb goes off tells you that the explosion should begin at the center. But that is not what happens in the double detonation scenario. Instead, the explosion begins on the outside, on the very surface of the star, in a thin skin of material that was not even part of the original star, that was assembled over 1 million years from the outer envelope of a nearby companion. The trigger is external in a very literal sense. It is stolen. It is delivered. And when it finally ignites, it does not simply flare and fade. It sends a shock wave inward through the star that reaches the deep interior and forces the core to detonate as well. The core did not ignite because of anything happening in the core. It ignited because of what happened on the surface. The direction of causation runs from outside to inside. The star's own interior fuel, the enormous reservoir of carbon and oxygen that it could never ignite on its own, is ignited by the shock wave of the surface burning, propagating inward from a direction the interior had no defense against. This is what the sequence really is. A white dwarf that detonates from the outside in. Not because the whole star burns uniformly from its surface toward its center like a fuse burning down. The reality is more subtle than that. The surface detonates first. A shock wave then races into the interior. And that shock wave, either by converging at a deep point, or by pressing against the shell core boundary, or by some combination of these effects, produces a small region where the core finally ignites. The core detonation, once it begins, then propagates outward again through the rest of the star. So in a sense, there are two detonations, one moving inward as a shock, and one moving outward as a burning front, and they meet somewhere in the interior at the moment when the second detonation is triggered. The end result is that a dead star, an object that had no way to ignite itself, that had been sitting quietly for perhaps 1 billion years, cooling and dimming and doing essentially nothing, is destroyed. Not by anything within itself, but by an outer skin of stolen fuel that finally reached the ignition point, and by the shock wave of that surface burning, which reached inward and forced the interior to detonate as well. The star that could not explode on its own, that could not access its own vast reserves of nuclear fuel, has been made to explode by an outside agent. And in doing so, it has produced one of the brightest events in the universe. A flash of light that will be visible across billions of light years for weeks and months. A cloud of expanding debris that will eventually mix with the interstellar medium and become the seed material for new stars and new planets somewhere else in the galaxy. Iron and nickel and cobalt and silicon and calcium, forged in the double-detonation, will drift through space for hundreds of millions of years and eventually be incorporated into the next generation of stellar systems. And somewhere, perhaps, on a planet forming around one of those future stars, iron in the core, calcium in the bones of living creatures will trace back through a chain of cosmic accidents to the exact moment when a dead star with no fuse of its own was ignited from outside by the helium a companion could no longer hold. It was a corpse that could not burn. It was made to burn anyway, and in the burning, it seeded the universe with new material, new possibility, and a story that begins on a stolen surface and ends in the total destruction of everything that lay beneath.